Hello, everyone. So we're spending a second day on topics 3.7 and 3.8. Topic 3.7 is all about solutions and mixtures. And the main thing that I need you to be able to do and accomplish with this is to do calculations that are surrounding concentration. Okay, so we practice this quite a bit. So I'm on page 31. So please turn there and follow along with me. So we practiced this in class, but we had a couple of big equations and concepts that we're working with as far as concentration goes. So if you are here in class, you got these notes down, then please just listen for a little while we review this, because these are going to be really important concepts. If you were not here, though, make sure you're writing this down, following along with me. So first off, concentration is the moles of items going into the solution divided by the liters of solution. And we call this molarity. So concentration is the same thing as molarity. The units for molarity are capital M, or, so we could have capital M molarity, or moles per liter. Moles per liter, and they mean exactly the same thing, right? Now, with this, I'm going to switch to a black pen. There's a really common rearrangement of this equation. So we have molarity is equal to moles divided by volume in liters. And it's using this information to solve for moles. So if I take volume times by that concentration in molarity, then that will equal the amount of moles. Okay? So if they provide you with two of these three things, whether it's concentration, volume, or moles, then you can figure out the third. And then we described in class how this equation could also be used to describe the, dilution of a solution. So we could make a solution less dilute, but the number of moles is not changing. So like if I have a container and I have a certain amount of moles that are in a solution, and then I want to dilute this, I would just add more water in there, more distilled water. But the amount of moles doesn't change. So you could say whatever the moles were initially, it has to equal what the moles were finally. And we know that moles is volume times by that concentration times by the molarity. So M1V1, because that would equal N1, right? The concentration times by the volume initial would equal the moles initial. That has to equal M2V2. So if they're talking about diluting a solution, then this is the equation we want to use. If they're just providing you with a concentration or moles or volume, then we're just using the first arrangement of this. Okay? And the last thing I want to point out is that we can, or that we often see that we use brackets to represent concentration. So if I want to say the concentration of salt, sodium chloride, in a solution, that would be the moles of that salt divided by the liters of solution, okay, divided by that volume. But we do it in liters, okay, volume in liters. And you guys are already familiar with mole fractions. You've been doing that. Okay, when we were in class, we did these three problems last time, and we did them together, and then we went into the problem set, and you guys did a couple that were very similar to this on your own. Okay? So if you were not here in class, that's what I need you to get done. So I need you to try questions 1, 2, and 3 on page 32. And then in addition to that, I need you to do question number 2 on page 34. Here's the key to help you. Then I also need you to do question number 5 on page 35. So there's the key to help you with that one. And then the last one that I want you to do is number 4 on page 35. Again, there's that key. You can pause this and use this to help you. So if you weren't here, maybe you're doing the opposite, where you're using this key and looking through how to do those questions, and then you're going back to page 32 and trying these 3 on your own. Thank you for those of us that were here and got this done during class time. Okay. Now, here's the new stuff. So first off, we need a reminder about which one's bigger, a cation or an anion. So reminder, cations are positive and anions are negative. And what makes them positive and negative is gaining and losing electrons. So cations, they lose negative electrons. That's why they become positive. Where anions, they gain negative electrons. So that's why they become negative. If we lose electrons, the radius gets smaller, but if we gain electrons, then the radius gets bigger. So if I was going to draw a particle model of sodium chloride, NaCl, we know that our metals, and based on its location, we know that sodium is Na+. Metals lose electrons, and nonmetals like chlorine gain electrons. So if we are losing electrons, the radius is going to get smaller. So if they're asking you to draw ions, we need to see that the cations are smaller and that the anions are bigger. Okay. And because they're smaller and bigger, that's why they can create these like repeating patterns here. Okay. So if I show you this model and be like, this is sodium chloride, then you can point out which one's sodium and which one's chlorine. Be like, oh, the smaller ones, those are sodium, and the larger ones, those are chlorines. And because we get this alternating of big and small, they create these like crystalline structures with this pattern of ions in there. Okay. How would the chosen cation and anion above arrange around a water molecule? Draw an example below. So if we have a water molecule or any polar molecule, we should think about this for a minute. Here's my water molecule, and there's 2 things going on. The first thing is that we got these lone pairs. So this definitely creates a negative region of this molecule. And then we should also think about the electronegativity of the atoms. Reminder, electronegativity is the ability, the strength an atom has to pull on or try to take electrons away from other atoms. Noble gases are non-reactive. So they really have low to no electronegativity. Like they're not trying to gain any new electrons. But if we ignore the noble gases, fluorine has the biggest electronegativity. It's the bully of the periodic table. It's trying to take everyone else's electrons. And this is the general trend for electronegativity. So as we go from left to right, we increase in electronegativity. And as we move from the bottom to the top of the periodic table, we increase in electronegativity. So in our water molecule, we got hydrogen and we got oxygen. And look at how close oxygen is to fluorine and how far away hydrogen is. So oxygen is much more electronegative than hydrogen. So if we're thinking about these shared electrons, the oxygen pulls more on those shared electrons than the hydrogen does. So we get these dipole arrows. Like the electrons are spending more time with oxygen than they are with hydrogen. So that would make this region even more negative. And if the electrons are moving away from the hydrogens, then this makes this side of the molecule the partially positive region. Okay? So what if I have like sodium Na cation, and it's smaller, but how would water molecules arrange around this? If this is a positive ion, then the negative region of a polar molecule would be attracted to that cation. So I would see water molecules surrounding this ion, with the oxygen being the one that's pointed towards that ion. And then from 3.1, we know that this would be an ion dipole interaction. The attractive force that would be occurring, that IMF, would be an ion dipole. Okay, what about if it was chlorine though? So I'm going to draw a larger Cl minus. How would the water molecules arrange around the chlorine? Oh, the positive hydrogens. That's what we would see being attracted towards the chlorine. Okay. We'll even go like that. So that's what we'd want to see here. We'd want to see how the hydrogens are the ones that are being pulled closer to the chlorine. It wouldn't be the oxygen. Great. Last thing for this video. Good, we'll keep this one short. There are so many particle diagrams in AP Chem. And first thing I want to point out, with particle diagrams, you should think about how many moles are in something, or really we're going to pick something to represent a mole, and then we got to think about the volume. So this is a great question here, and if you look at it carefully, we can definitely figure this out. So it says beaker X and beaker Y each contain 1 liter of solution. So if I'm looking at this represents 1 liter, and this represents 1 liter, as shown above. A student combines the solutions by pouring them into a larger, previously empty beaker Z and observes the formation of a white precipitate. So we observed the formation of this white precipitate that's down here, but the question says it adds them together. And this is important. Look at this. If this represents 1 liter and I pour that in there, and this represents 1 liter and I pour that in there, and the size, oh, this is not 1 liter. This is 2 liters over here. Assuming that the volumes are additive, 1 liter plus 1 liter equals 2 liters, which of the following set of solutions couldn't be represented by the diagrams above? What do we have going on in beaker X right now? Oh, a polyatomic ion, everyone. You need to know these polyatomic ions, because if you can't see it, it's hard to determine the amount of moles. So it has, sorry if you hear my son in the background, he's making some awesome crafts while I'm doing this video. So we have AgNO3 silver nitrate, and there is 1 silver to every 1 nitrate. Okay, so if I were to look at this right there, that's a 1-to-1, right? I have 1 silver and 1 nitrate. Let's see how many of these like silver nitrate binary compounds we have. So there's 1, 2, 3, 4, 5, 7, 8, 9, 10. Okay, there are 10 of these silver nitrates inside the 1 liter. And just based on the answer options, because look here, our only answer option for silver nitrate is a concentration of 2 molarity. So 2 molarity on this image must be represented with 10 of the items in 1 liter. Okay, what about MgCl2? So 1 magnesium and 2 chlorines. Let's circle these and see how many combinations we have. 1 magnesium and 2 chlorines. So there's 1 combination, 1, 2, 3, 4, 5. Oh, so there's only 5 of these in the 1 liter. And remember, and the only reason why we know this is because the image is showing us 10 silver nitrates in 1 liter, and the only answer options possible are 2 molarity. So 2 molarity must be these 10 items per 1 liter. And so now we've got 5 items in the 1 liter. So that's half as much. So that must be only 1 molarity. Oh, so that narrows us down right here. Okay, I'm going to have you take it from here. I'm going to have you look at what's happening over here. Remember, it's 2 liters, not 1 liter. And then pick an answer option between C and D, and then we will talk about it during class time. And I'm going to be asking everyone before we dive into it which one we're choosing, to see if first you're watching the videos and you're taking these notes, and then I'm curious to see as a group before we come to class like which one we are leaning towards. Okay, everyone. Shorter video today, which I'm happy about, and we just need lots of practice, so that's going to be next class. Like lots and lots of practice with those calculations. We were tired because it was the day after Halloween, so we need to get that practice in. And then these particle diagrams. Like, they're not difficult, but you really have to be careful and like analyze what it is you're looking at and what it could mean based on the question or even the answer options. Okay, thank you all so much for your hard work, and then I will see you in class on Tuesday.